那个 Chen 来给我这个演讲。那这个 Fargues-Fontaine 他是Berkeley 的 PhD 嘛，他毕业之后现在在 Cornell 工作这样。那sorry， 我不晓得我要当那个 host， 所以我没有把这个开头记起来。那你就那我们就欢迎这个 Chen。
Thanks for inviting me to speak. Right, so I guess I'll write the title so that categorical Langlands, and also coherent Springer theory. So it's unclear if I'll get to talk about coherent Springer theory today. I mean, somehow we think of these as somehow the same, but right. But I'll sort of come at it from a perspective of categorical domain Langlands. So before I go into the categorical version of the statements, I should probably say a little bit about the decategorified statements. So let me know if you have a question, feel free to interrupt me. Okay. So let me just sort of set up some notation. And, so I'm going to take G to be a reductive group, and I want it to be split over F, which we'll take to be a local field. So if you know what these will mean, that's fine. So for example, one could take F to be the p-adic rationals, or a finite extension of it, or we can also take large series of finite fields. Well, there's one condition to say, so this should be a local field, it should be non-Archimedean. So I wanted to have finite residue field. And let me reserve K for something else. I'm just going to say this in Okay. So what kind of questions do representation theorists ask? Well, given any group, you can ask what are the irreducible representations. So the sort of local Langlands conjecture proposes what it does is it proposes a classification of the irreducibles of the group in this finite field. I just kind of want to remark that this is, this field is truly huge, and sort of somehow where the difficulties in this problem come from. And so what's the statement? So if I take irreducible representations, I'm going to sort of decorate it with some basic sort of coherence condition. So it's smooth representations, which are irreducible. So you can ignore what smooth means. Of the group with coefficients in this field. So there should be some map which surjects onto a set, which I'll call the Langlands parameters for the dual group. And so this is the dual group of G. It's what we get by sort of swapping roots with co-roots. So I don't know how, I'm not sure how familiar, but so if I have SL in here, I get PGL in here. Okay, so yeah, the conjecture says, okay, well I should say what the set is. It's a set of maps out of the Bay group into the dual group with coefficients in Q all bar. Here L should be different from the characteristic of Q. And I need some conditions. So I want this to be, so this should be a group morphism. It should be continuous. So there's a natural topology. Okay, so what is this group? You can think of this as something that's dense. It's just some dense subgroup of the Galois group. Okay, and it comes equipped with a natural topology. And I need this to be finite in the sort of p-adic topology on this side. And okay, and I need the Frobenius, so I need any lift of the Frobenius element to go to a semi-simple element over here. Okay. Any questions about maybe? Well, okay. So I said this map is surjective. so that might be a little unsatisfying because the fibers would be huge. But part of the conjecture is that the fibers are finite. And there are refinements of the conjecture that actually attempt to give a description of the fibers, which I won't get into today. But they're sort of, these are called L-packets. And they should have something to do, I'll just draw a squiggly arrow, they should have something to do with irreducible representations of component groups of stabilizers. So if this is my Langlands parameter, i.e. One can kind of, at a very sort of coarse approximation, think of the Langlands parameter as just certain elements in this dual group that satisfy relations coming from the Galois group. So such a thing has a centralizer, and I can take a component group of centralizer, irreducible representation for it. So it should have something to do with these irreducibles, the irreducibles for this group. Okay, Okay, so today I'm only really going to talk about the sort of principal series part of the Langlands conjecture. So what I want to do is I want to restrict to sort of subsets on both sides and sort of prove, I'm going to restrict to subsets of both sides where we actually have theorems that sort of confirm at least sub-conjectures of local Langlands. So the name that this goes under is the Langlands. And so the Langlands, it was their conjecture, and it was proven by Kastan and Lustig, and also Ginsburg had So what does the Langlands say? Well, what I'll do is I can on this side I can take the irreducible representations that are generated or that have an Iwahori fixed vector. So I'm going to use this notation. So the Iwahori, we want to think of this as some kind of analog, some sort of affine analog of the Borel. So that's sort of a reasonable first approximation. And so I'll sort of write the definition. These are the irreducible representations such that the Iwahori fixed vectors are not zero. So another way to think about this is these are the representations that you get by inducing from the trivial representation for the Iwahori. Okay. And then this there's an expected surjection onto maybe, I'll just kind of explicitly write what the parameters should be. They should be semi-simple elements. Probably not that notation. And now I'm going to take complex coefficients. I'll sort of remark on why we can do that in a bit. So I want a semi-simple element and a no-potent element such that when I conjugate the no-potent element, it's scaled by Q. So Q is the sort of order of the residue field. Okay, are there any questions about this? So, yes.
So it's kind of when, for example, when G is at 0, 2,
yes.
then it's kind of corresponds to the spatial representation, or
Sorry? Special representation?
Yeah. In the case, because you have Q there, so it's not a principal series, or.
Well, I kind of vaguely think of this as principal series, but by like definition or something. But it might, I mean, maybe other people have a different notion of what that means. I mean, so maybe I don't know. So maybe I can say like you can get even smaller. You could look at the sort of the unramified part. So somehow like there's a thing that happens in for these p-adic or hoop groups that doesn't happen for like complex representation theories, which is like you can look at things that are sort of induced right, so this is, you know, this is like G QP or something, this is like G VP or something, right, and this kind of thing, yeah.
So your I can be allowed to be the maximal constant?
No, so I is in Iwahori. I is in Iwahori. Yeah, only, yeah, I is in Iwahori.
The direction set is already about the dual group, because the check.
Yeah, this is about the dual group.
So you're going to explain the map?
Am I going to explain the map? In some sense, yeah. So, okay, so, yeah, so maybe for the first half, maybe it'll take a little more. I'd like to sort of overview. I would like to go over the sort of proof of this theorem. So this is a theorem. Let me skip the part about the L packets. I'll mention it later. But yeah, so this is now a theorem, and I would like to sort of say a little bit of how the proof went. Okay, so I need a little bit more setup. So the point is, like, the proof of this thing, the proof of this theorem used a lot of geometry. So let me so I need to sort of set some things up. So I'm going to take n tilde, this maps down to n. I'm going to denote this map by mu, and this is going to be the Springer resolution of singularities. So I'm going to kind of stop decorating things with G's. Okay, well, right, so this is NG check, and this is Springer resolution G check. Okay. So what this is these are pairs of no-potent elements and Borels such that the no-potent element is contained in the Borel. Maybe a less so when we sort of write it this way, it kind of looks more invariant, but one can sort of choose sort of your favorite Borel. So if you have a favorite Borel, you can choose a base point, and this becomes sort of maybe like in type A, this is pairs of a no-potent element and a flag, such that the no-potent element fixes the flag.
So in the first line, the X in the cal B or U to B? I mean.
Yeah, so that's a cal. Yeah, that's like this is like the variety of Borel.
Yeah.
Yeah.
And then excising. I mean.
Sorry. Thanks.
Yeah.
Okay, or yeah. So this is the Springer resolution. Given this, I can define the Steinberg. Okay, and then just a remark, just so you have a sense of what this is a union of conormals, the Bruhat orbits, i.e., sort of G acting on a pair of flag varieties. So I can kind of write this a little more explicitly. These are triples X, a Borel, and another Borel. Such that X is in both. So sometimes this is called a variety of triples. Are there any questions on that? Okay, so let me make a definition. The mixed affine hectic category is the derived category, so I'm going to denote it with a bold H, with an M, and this is going to be the derived category of coherent sheaves on the Steinberg stack with an extra GM action. So if you like, this is just the derived category of G cross GM equivariant sheaves on the Steinberg variety, where the GM acts just by scaling the no-potent element. Okay. So one might ask, why is this a reasonable definition, right? Because, okay, so maybe remark, right? Sort of, usually, Peck algebra is something like functions on bi-equivariant functions on some group, right? So this might be an expectation. So you might expect the Peck category to be something like sheaves on the same thing. So there's a question of why is this thing deserving of being called an affine Peck category. So this theorem came long after. I think there was some expectation that this theorem came after Constantine-Lusik's proof, but right. So sort of there's a difficult theorem by Roman Desser-Kazakov, which says that this category of sort of L-adic sheaves on Iohori equivariant L-adic sheaves on the affine flag variety with dual coefficients. There's an equivalence of categories between this and the derived coherent sheaves on the Steinberg stack without the GM action. So, okay, so to add in the GM action on the right, you need to say something about mixed structures on the left. I think that's still that's still a conjecture. Okay, so here's affine Peck category. We make another definition, which is the affine Peck algebra. So I'll denote this by curly H. This will be endomorphisms of the induced module from the sort of GF endomorphisms of the induced module from the Iohori to the group. This sort of the induction of the trivial representation. And equivalently, this is exactly what I wrote up here. It's Iohori bi-equivariant functions on the group. Sort of compactly sorted. Okay, so what's the point? So theorem. This is due to Constantine-Lustig. So the K theory. So somehow, if we sort of assume we know Roman's equivalence, right? The K theory of this is maybe not so bad to see, right? So the K theory of This is the Iohori Peck algebra, and the affine Peck algebra. So I'm going to denote the Iohori Peck algebra with a Q. So there's sort of an observation that one has to, if you sort of do some work and figure out what the generators and relations of this algebra are, you'll find that it doesn't depend on the field, it only depends on the order of the residue field. So it only depends on Q, and it does so in an algebraic way. So one can kind of assemble them into a family of algebras that vary depending on Q. So if you do that, you get the thing that I'm going to call the affine Peck algebra. Okay, so the theorem that Constantine-Lustig proved is that the K theory of this mixed affine Peck category is the affine Peck algebra. So that's sort of, okay, so that's the theorem. Now, how do we pass from this to like some statement about representations? Well, okay, so this is the first ingredient. The second ingredient is a kind of equivariant localization. So there's a sort of part of this statement which I didn't quite. So they give an equivalence here between the K theory and the affine Peck algebra, but they also identified a center. So the center of the affine Peck algebra is identified with the K theory of reps G cross Gm. I think I've forgotten to put G checks everywhere. I did this on Monday as well. This is something I will never get right, but okay, that's correct. Okay. So, right. So they identify the center, and if you want to classify irreducible representations of an algebra, one thing you can always do is specialize central characters. Right? You can specialize as central characters and then do your classification there. So, okay, so if we fix, so what are central characters? So a central character of the algebra of, right, so now this actually tells you exactly what the center is, right? It looks like, you know, functions on G mod G tensored with, you know, functions on Gm. Right? So a central character is just a map from this thing to C. Now C star because it's a character of an algebra, not a group. I.e., you can roughly think about this is it's a point in the adjoint quotient across Gm. Right, and I'm going to take S to be like a S is semi-simple. So, right, the closed points of the adjoint quotient, the GIT quotient of G under the adjoint action are given by semi-simple orbits. You can choose there's a unique, the conjugacy semi-simple orbit in each. Yes.
So the automorphic C G quotient G or?
Yeah, sorry. Okay, so maybe I'll write this. It's functions on G that are G invariant.
Oh, okay.
Other. Right. So, good. So the statement of equivariant localization is that the K-theory, if I take the K-theory of the Steinberg stack, and this is a little, this is more general than I'm stating it, but I'll just state it in our case of interest. And if I specialize at the center, or if I, let me just kind of write this for shorthand, maybe B for classifying stack, at the given central character. So I'll call this the character. That's the corresponding point. This is just given by the Borel-Moore homology of the fixed points, of the S fixed points of the Steinberg. So this is the statement of equivariant localization. And now the third ingredient so I'll try to recap this at the end, or in a few minutes, but let me just say the third ingredient is that we know we have a sheaf theory for Borel that computes Borel-Moore homology, right? We use sheaf theory. That is to say, what we know is that the Borel-Moore homology of any space, any reasonable space, this is just given by the global sections of a sheaf which we call a dualizing sheaf. Right, and we have a six functors formalism due to growth. So sort of a Grothendieck six functors. We can express this. This is just the sort of the X groups from the constant sheaf into the dualizing sheaf. And then you can start to like push around the junctions and put base changes, completely formal sort of results in sheaf theory. So let me just do one step. So for example, this is some kind of star pullback, and this is a street pullback. So I can write this. Right, I'm just going to make up notation. Right, so I'm just going to pull back the constant sheaf from N. This is like a street pullback with the dualizing sheaf on N, in tilde. And then I can use an adjunction to get this. So, okay, so I can move this over here. Right, now you apply base change to this thing, and then you apply another adjunction. And at the end, what you get are the X of the push forward of the constant sheaf of the fixed points with itself up to a shift. Let me just put D on the shift. Okay, so there's some shift which I'll ignore. Okay, but the point is, Borel-Moore homology are the derived endomorphisms of some object, some sheaf. And then you apply BBD localization. Right, so what is that? That tells you exactly what this, well, it doesn't tell you exactly, but it tells you what this thing is, right? It tells you that this thing is a direct sum of simples. With, so some simples sort of that are attached to some orbits. So this is something like an orbit plus a local system tensor some coefficient vector space with a shift. And then just formally from this, right, what you find is that there's the irreducible representations of this algebra, the Borel-Moore homology, which I'm going to write it now. It's the affine Heck algebra, right? So this was the affine Heck algebra, and this is the specialization at a given central character, are exactly in bijection. Well, what they are the set of these that appear. That's just how it appears. Okay, so, right, because if I take endomorphisms of this thing, these are simples, right? So you get nothing. And these, well, they're extensions, but we can ignore them because we live in the radical, and then I just get endomorphisms of these. So, right, so the irreducibles are just somehow given by these vector spaces, these coefficient vector spaces. And, right, so what does this have to do with those, those semi-simple, those commuting elements from before? Well, remember, what was S, right? S is something like, well, I think I used S before, but it's something like a pair of a semi-simple element in Q. And the points, what an orbit in here is just given by a no-cone element that's fixed by the action of S and Q. So what it means for S and Q to fix a no-cone element, right, is just exactly that. When I conjugate by n and I multiply it by q, I get that n. So that's just the condition that we have to that they Q commute. Okay, so that's the argument. It uses geometry. So the main, what are the three ingredients? First, we need some kind of we have this sort of affine Heck category, and we have a sort of automorphic realization of it. We have a realization of it on either side of Langlands, and one has to somehow identify some decategorified version. Right, so this is a decategorification. Right, so this is somehow on the sort of Langlands parameter side, and this is somehow on the representation theory side. Right, just by the way that I defined them earlier, and one has to identify these two. Right, so that's the first ingredient, and then the second is to apply localization to sort of fixed central characters, and then you just have a sheaf theory that does the rest for you. Okay, are there any questions? Okay, hopefully I haven't bored too many people, but okay, so great. So maybe let me mention the categorical forms of local Langlands. So if one wants to categorify local Langlands, there's kind of a natural thing one might try to do, right? So on one side, one can just look at representations, like the category of representations. Right? On the other side, one has this set of L parameters, which one might hope, and in fact it does, assemble. So one might try to sort of define, so maybe. So what is this thing? This is some kind of moduli stack of L parameters. And just very naively, it's, you sort of write down the moduli problem, and of course, there's some, if I do the work of various people, and Schulte, Chen, I think maybe Buzzard B. Anyway, right, so there are various constructions of this moduli stack, and one might hope that these two give you an equivalence of categories, but in fact they don't. So the reason is somehow that this category is too small. And let me sort of rectify the statement. Well, let me give you one version of this. So when here's sort of the conjecture. So a categorical local Langlands conjecture it's like this. So we have sheaves on GF, mod GF, where this is an adjoint quotient twisted by Frobenius to all bar coefficients. There's an expected equivalence between this category, the category coherent sheaves, on this stack of Langlands parameters. Okay. So categorical deleting Langlands. Let me just make a remark, right? So sitting inside of this category, if I just take the orbit sitting at the identity, right, everything fixes it, so that's going to look like smooth representations. I don't know if that's literally true, but you know, up to some sort of twiddling with this category, there's an expectation that you have this. Right, so maybe an easier form of the categorical local Langlands conjecture would be to find fully faithful subcategory of this category equivalent to representations for GF. So now let me doing that, I can kind of state our theorem. So theorem, this is our paper, right, which is that there's a sorry, it should be a derived category. So there's a fully faithful functor from the category of the derived category for the affine Heck algebra into the category of unipotent Langlands parameters. So this is the connected component of L, which contains sort of the trivial L parameter. And well, sorry, this is quite true. This is true if I define something differently. If I specialize that Q, then I get on this thing. And let me give a sort of explicit definition of this stack. So LU G, it's going to be given by a fiber product. So it's going to be the fiber product of the nopone times G M. Right, so there's two maps. One is at, and one is the projection. So it's the product of these two maps. And then I want to map it from the diagonal. And this is just the stack. These underlying points are elements of G, nopotent elements in Q, such that when I conjugate, I scale by Q. So now here, I just want to remark, S does not have to be semi-simple anymore. Somehow, if the semi-simple elements of a group don't form a scheme. Okay, that's the statement. Okay, so how do we prove this? Or like, what's the idea of the argument? Maybe better to say. So, where do categorifications come from? So, well, sorry, that's probably not the right word, but like, how do I lift the statement to a level of category? So there's some precedent for this. So this is a result to various people, but in particular, I think writer Russell and Lustig, and probably, yeah. Anyway, so right, which is that. So earlier I wrote down this isomorphism. The Borel-Moore homology of the Steinberg stack is equivalent to the X of the Springer sheaf. But sort of this calculation is only on the level of homology. So what Ryder and Russell did was they showed that this is actually equivalent to DG algebras. So just by pure formalism, what that says, right, is that what I can do, this lives in the category, the derived category of perverse sheaves, or the derived category of constructible sheaves on the no-cone cone, which are equivariant. Right, so there's an object in here called the Springer sheaf, and the subcategory generated by it is by formalism given by modules. Well, it's given by the DG algebra and the morphisms of the object. And by their result, this is just given by Borel homology of the Seinberg. Sorry, modules. Derived category modules. Right. So here's a kind of categorical statement, and the way that, and the sort of key thing we needed was we needed this kind of sheet theoretic expression of the algebra that we were interested in. Right. So the key ingredient, some kind of sheet theoretic description of the Borel morph of the algebra. Okay. So the question, one question you could ask is, do we have the same thing for the affine-Hecke algebra? Right, so if one were to sort of just naively look for such a statement, what one might want is, one might want that affine-Hecke algebra to be the global sections on, the Seinberg or something of some sheet. Okay, so our identification of the affine-Hecke algebra came from K theory. Right, it came from the K theory of this stack. So maybe what we're asking is, we want the K theory of maybe generally a space or something, or a scheme or a stack, to come from the global sections of some kind of sheet. And this seems a little bit unrealistic, perhaps. Like, yeah, I do not know how one would get something like this. I mean, one can. It might be possible to do this, but first, there's sort of two obstructions. One is like, first, this thing, when all these statements only work when I do derived, when everything is derived. I take sort of derived endomorphisms, and I take sort of homology, which is like really about a derived category. But here I've taken only K theory, so I've sort of thrown away sort of K1, K2, or I've thrown away the higher K groups, and also those things are something, and the higher K groups are truly, they're not zero, and they're kind of difficult to understand. Another problem is like, I just don't know where this would come from. Okay. So the sort of key idea is to replace K naught with functional homology. Namely, and I'll hopefully get to this. So, Hopf homology. So, what is it, right? So, on the one hand, so Hopf homology has a sort of abstract definition that kind of gives it two realizations. So, one of them gives it a realization which one can think of as kind of a categorical invariant. I kind of like to think about this as being algebraic. Right, so, Hopf homology is some machine you can throw a category at it, give you a chain complex. Right? On the other hand, based on this abstract definition, which I'll talk about in a bit, it also has a geometric realization. So it also has a geometric realization of the global sections. So if the category is like sufficiently geometric, on something I'll call the derived loop space of X, of some kind of sheaf. So maybe the structure sheaf, maybe something else. We'll kind of discuss those details later. But the point is, sort of functional homology has all these properties that we kind of wanted, right? That one might hope would lead to sort of categorical states. Are there any questions? So let me first sort of say a little bit about the definition of functional homology. So let me sort of say what it is as a, well, so definition. So let's say I have a monoidal category. There's a notion for what it means for an object in the monoidal category to be dualizable. Right? So if I have an object which is dualizable, if, well, there is a dual plus what do I need? I need a identity map, right? So I need a co-evaluation. So I need something from the monoidal unit to X tensor X dual. I need an evaluation map that goes the other way. And I need these to satisfy some identity. So this is what it means to be dualizable. And if you just take U, so here's the first example. If I take U to be vect, then I just get like finite dimensional vector spaces. Right? Dualizable means finite dimensional. Because somehow if you're not finite dimensional, you don't actually have, like the identity map of an infinite dimensional vector space doesn't live in the tensor, and the d-tensor dual. Then you have the infinite one. Okay. The example that I'm interested in is I want to take U to be the category of each categories under tensor product. And in this case, right, dualizable, well, there are some characterizations of it due to, I think, Grinfeld, but one example, or let me write it this way. So if the category is compactly generated, then that means it's dualizable. I.e., most categories that you run into in life will be dualizable. And then we define the Hawk's homology of a category to be the following thing. So if I have a category, so the monoidal unit here is chain complexes. Okay, so I have a co-evaluation map from the category to tensored dual, and then I also have an evaluation map. And the Hawk's homology is what you get by sort of taking this composite and applying it to K, the one-dimensional vector space. Look, this might seem a little arbitrary, but let me just make a few remarks. First, when I said DG categories, I didn't say what the morphisms were. So I really want morphisms that are continuous, like commute with colimits, which means every functor that commutes with colimits from, chain complexes to chain complexes is just tensoring with something, right? Because every object here is just it's a stupid colimit of the one-dimensional one. So this really actually determines the functor. Okay, so that's the definition of functional homology, and it's completely abstract, but you can kind of, so the point is, if I just choose a dualizing structure, if I choose a dual for my category, I get the calculation of the functional homology. So sort of method one, or maybe approach one for how to compute this thing, is to use Cohen's DG Morita theory. And if you just sort of work this out, what you get is the usual cyclic bar complex. Or, you know, if your category is just like an algebra, if it only has one object, then you get that the Hopf homology of your algebra is the familiar thing where you sort of tensor the sort of diagonal bimodule itself in a derived way, of course. So and then, well, there's also a way to sort of say what this means for a category quite explicitly. And so using this method, you kind of have a way to compute the Hopf homology of a category using its categorical structure. So the second method I'd like to talk about is due to Bensby, Nadler, and Francis. This is due to Bensby, Francis, and Nadler, which is the following. If we take the category to be something like category quasi-coherent sheaves on X, then C is self-dual. So the dual is also Q co of X. And, okay, so what are the evaluation and what are the co-evaluation maps, right? So the monoidal unit is just quasi-coherent sheaves. Sorry, this is derived categories. I've drank the Kool-Aid, so I don't write D anymore. So derived category quasi-coherent sheaves on a point, right? This should go to Q co X tensor Q co X derived category. So there's an identification of this with the derived category quasi-coherent sheaves on the product. And the way it goes is it just goes by it's the exterior tensor product. And then I need an evaluation map. Okay, so what are these maps? Well, you can think about this somehow. How should one think about this category as endomorphisms of the category quasi-coherent sheaves on X? Well, you can think about them as via integral transforms, right? If I have a sheaf on here, right? If I have a sheaf in here, I can define a functor in the following way, right? I can pull back, tensor with the sheaf, and then push forward. Right, so I can do a sort of integral transform on this. The sheaf on here defines an integral kernel, which defines an integral transform. Now, so the identity functor is the diagonal. So how can I express the diagonal? Well, it's the pull. What this should do is it should take k to the diagonal. Structure sheaf on the diagonal. One way you can kind of write that is it's a push, it's a pull, and then a push. Right? It's a pull from the only map to a point, and then a map to the diagonal. The evaluation map, what it should do is it should have the property that it take E exterior tensor F and take this to Hom EF. Maybe it's putting a dual somewhere. And one way you can formulate what this is, it's the map pulling back from the diagonal along the diagonal, and you push down to a point, i.e. you take local sections. So this is the part where things get a little weird. So kind of, in order to formulate this geometric statement, one needs to pass to the world of derived algebraic geometry. So somehow, what I want to do is I want to do a base change, right? The push and then the pull should be a pull and a push. But, right, so I'll just define the derived loop space to be the self-intersection of the diagonal, and I'll make some remarks about it. Right, because this is a little bit weird. So, let me give some examples. So this is the derived loop space. It's also, maybe some people call it the derived inertia stack. So if we remember what the inertia stack is, a stack is like a scheme that has automorphisms attached to points. And the inertia stack of a stack is just given by pairs of points plus automorphisms. I.e., what it is it's a point of x. Like, what are the points of this thing? It's a point of x, another point of x, and then two identifications of those points. Right? So if I identify one way and I identify another way, the first identification you can think of as saying this is the same point, and then the second one gives you an automorphism. So, like, what are some examples? Well, if x is a scheme, well, you don't have any automorphisms of points, right? So, classically, the derived loop space should just be x. But you don't have base change in classical algebraic geometry for maps that are not flat. And this map is very much not flat when x is a scheme. So you need to pass it we need to pass the derived algebraic geometry. So the way that this is kind of fixed, sort of formally, is to just, right, the problem with trying to execute base change for this push-pull is that you have tors, right? If one of the maps is, if the map you pull back along has no tors, then you're good, i.e. if it's flat, or e.g. if it's flat. But so if it's not, you're in trouble, right? But the way that sort of you can fix this using derived algebraic geometry is to build the tors of that tensor product into the space. So somehow this thing is a derived sort of scheme or stack. And you can kind of think about this as it has tors. It's like the data of the tors are somehow contained in this object. And one can kind of think about it as a geometric object. So in derived algebraic geometry, what is this? It's the derived spectrum of the derived symmetric derived sim of sort of scalar differentials of x, but I have to put them in degree negative. So just by convention, when I take sim of something in an odd cohomological degree, I'm really taking exterior powers. So this is the exterior algebra of x with no differential in negative degrees instead of positive degrees. So here's another example. If x is BG, right, then the loop space of BG, so for BG, right, the diagonal is actually flat. If you check it on a cover, you just get G mapping to a point. You just pass to the standard cover, which is flat, so G is smooth. So, right, so this actually has no derived structure, you just get the usual inertial stack, which is the adjoint quotient. And let me just say, the only examples that I'm really interested in are derived loop spaces, quotients, global quotient stacks. And in this case, what does it look like? So we have a map like this, mapping down to x cross x, and this is the action map times the product. So just some sort of formalism, we'll just do this. And if we just sort of observe, what are the points of this thing? There are pairs of points x and g such that g fixes x. So sometimes this is called like a universal stabilizer, or maybe universal fixed, depending on which thing you're projecting to. Okay, so I'm close down time, but I just want to sort of observe that that unipotent that stack of unipotent Langlands parameters from before is exactly the derived loop space of the nopotent cone mod G cross GM. Right. So sort of here. So somehow our search for the sheaf theory for the affine Hecke algebra has naturally led us to the parameter space of the representations. Okay, so let me just wrap up. So where am I going with this? The point is, I erased things. So the point is the Hopf homology the derived category quasi-coherent sheaves on X by that whole push is just given like global functions on the derived space, which is exactly what we wanted. We wanted it to be global sections of some sheaves. Likewise, there's a homological version of this theory, which is instead of QCO, you have INCO. And this is going to be the derived sections of some kind of dualized sheaves. So we'll get into what that means. But there's a theory sort of developed by Gates-Ferry, Rosenblum, and others. Okay. So now in this setting, one has the same, not exactly, but you have some limited version of the six functors formalisms, and in particular, you can just use the same formal adjunctions and base changes, and what you get is that this thing is the derived endomorphisms of the loop space of the Springer resolution, and I'm going to push forward functions on the stacky Springer resolutions. Okay, so the same calculation that we did for sheaves, now we can do for Hopf homology. Okay, so the point is we have two calculations of Hopf homology. One comes from geometry. Right? It comes from the sheaf theory. It comes from thinking about. Well, it comes from this sort of presentation of Hopf homology as global sections of sheaf on the loop space, and let me replace X with Z here. Somehow, so Z is X crossover Y X. So in this sort of general convolution setup, sorry, I messed this up. So in this setting, right, when it looks like a convolution category, I have that. So this first line was always true, but in order to like identify, it needs to look like a Steinberg. So this is what I get. On the other hand, I have a categorical calculation. So here's a theorem, so this is due to us, which is that we can calculate the Hopf homology of the mixed affine Hecke category, and it's exactly that by Hecke algebra in degree 0. And somehow sort of vanishes outside degree 0. And this is probably extremely untrue for sort of algebraic theory. So because we have two ways to, like any two calculations of Hopf homology give you a canonical equivalence between them. What that means, right, is we have an identification of the affine Hecke algebra with the derived endomorphisms on the loop space of the stacky cone of this loop space version of this sort of push forward of the structure sheaf of the Springer resolution. Right, so this is what we call the coherent Springer sheaf. Okay, and then I'll just wrap up. If I take, right, just again by formalism, that means the derived category of H modules is equivalent to the subcategory generated by this object. Inside of the derived category, I guess I need to go big, so incoherent sheaves on the loop space of the no-point cone. And, okay, that's sort of the gist of how we sort of get that kind of statement. Okay, I think enough time, so I'll stop here.
Question? So, any question?
So this G is complex and simple. I would like to have homomorphism of G and the G dual. Is your L and over G cross G similar to that?
Sorry, could you repeat that first part? You wanted maps from GM into G dual.
Yeah.
I don't think so. I think this is adding the GM in is like, okay, so the problem is like, the reason you need the GM is like, if you don't have it, right, you have like sheaves on this thing, it's coherent sheaves on, you know, it's coherent sheaves on site number V, and somehow like, if you take the K-theory of this, you just get, if you take K-theory, you just get the group algebra for the affine algebra, right? It's just like how when you sort of in the finite setting, you get the group algebra for the File group, but in the finite setting somehow, that family, every fiber is, you know, somehow, the finite Heck algebra when I, at a sort of specified Q is just, there's an isomorphism between that and the group algebra for the File group, so there's no difference. But in the affine setting, that family is non-trivial. So you really need to, you know, so in order to get the equivariant Heck algebras, one has to somehow add a GM here and add some mixed structure here. So I can say like what is the action of Q over here? It's given by the action of Frobenius. So another way one can think about this is one has to take the trace on the automorphic side. One has to take the trace of the Frobenius. Like this thing, I lied a little bit. This is I messed up. So like it's G with coefficients in F bar, Q bar, Lorentz series, T. Right. So this is something happening in the algebraic closure. Right. It's like a truly geometric thing. The path from FQ bar to FQ, one has to take the trace of Frobenius, and that's what matches on the side with Q. But somehow you can sort of treat them all at once because the action of Q kind of comes from an action of Q. I don't know if that's answered.
I'll ask you that.
Okay.
Maybe this question. So the whole theory doesn't depend on the characteristic of your local field F. It works for KT and F2.
So I mean,
are there any?
Yeah. So the theory kind of happens. So the way we pass, actually, somehow we don't really ever use the. Yeah, somehow the statement is true for affine Heck algebras, which kind of treats them all at once. And if you wanted to get some statement about local fields, sort of G in like a p-adic group, you would specialize at a Q. Right? So you would specialize affine Heck algebra at a Q, and that corresponds to some geometric specialization on this side.
So the characteristic of F doesn't.
Oh no, yeah. So the character it works in both sort of characters to P and character.
Okay.
Yeah, somehow like the affine Heck algebra is insensitive to that. Or the equivariant Heck algebra. Yeah, somehow that's the only thing we use presentation, the Bernstein presentation of the equivariant.
Other question?那我们谢谢。